So we're going to review vectors and start talking about lines, planes, and the rest of them. So our objective for today is review vectors, and then we're going to move on to lines and planes. Lines and planes. Well, we are still in chapter 12. Recall that we started from one dimension, line, into 2 dimensions, planes, and then we generalize this guy to 3 dimensions or the space. So 1D to 2D to 3D. Can we generalize this to 4 dimension, 5 dimension, n dimension? Of course. We have spaces with higher dimensions. Okay, perfect. So we denoted a line by R, plane by Cartesian product between R and R, or denoted by R with its dimension 2, and then the space with R, Cartesian product with R, and Cartesian product with R, which is denoted by its dimension R to the third. Very well. In each of these words, we can define some new objects. For example, in one dimension, they have the origin. And then they have some numbers. On the right-hand side, some numbers. On the left-hand side, positive numbers, negative numbers. And then in the plane, we can define new objects that we call vectors. Vectors in the plane. What are vectors? Vectors are mathematical objects that you can assign direction and magnitude to those objects. So vectors in the plane are mathematical objects with direction and magnitude. So suppose you have this vector in the plane, vector V. Sometimes we just leave this letter V vector as it is, or some other times we put a line on top of it to represent a vector. So if you open different calculus books, you might see just V, bolded V, representing the vector, or you might see V with a horizontal line on top of it, and this is vector. So for a vector V, we use the symbol which has X coordinate and Y coordinate related to the terminal point. This terminal point is actually a point in XY plane. Initial point, and the terminal point. So initial point, it's located at the origin. So initial point 0 and 0 And the terminal point as a point, it is, for example, x comma y. So note that for a point we use parentheses, but when it comes to a vector, we change the symbol. So when you open a book and you see parentheses, it means that it's representing a point. But when you see the symbol related to vectors, this is not parentheses. This is your vector. It shows that, hey, this vector has x component and y component, x coordinate, y coordinate of its, for example, in this case, the terminal point. So it shows direction. How do we find the magnitude? The magnitude of vector v, or absolute value of v, or sometimes we call it the norm of v, is equal to the square root of, we take the first component, raise it to the second power, we take the second component, we raise it to the second power, add them together. So we have the norm or magnitude of vector v, which is the square root of x squared plus y squared. Again, vectors in the plane are objects with direction and magnitude. We can say, hey, the length of vector v is denoted by, you can put it in absolute values. Sometimes they use double absolute value to show that we have the norm or length or magnitude of a vector. So we're generalizing the idea to these mathematical objects in 3D, and we define, for example, a vector like u here. Your vector u has components x, y, and z. Okay, with the same way, we can define the magnitude, norm, or the length of vector u as vector u to be the square root of x squared plus y squared plus z squared. So vectors, direction, and magnitude. So remember that when we have numbers, we're interested in adding numbers, multiplying numbers, creating, forming some new numbers. It's the same with vectors. We have some new objects and we're interested in creating some new objects. How do we do that? Well, we come up with some operations like addition, subtraction, scalar multiplication, dot product, and cross product. For these new objects, these vectors, we can combine them using the following operations. Okay, what operations? The very first one is addition. How do we add two vectors? So suppose you have two vectors and you're interested in creating a new vector. Let v be vector x sub 1, y sub 1, z sub 1. And your second vector u is vector x sub 2, y sub 2, and z sub 2. Can add these two vectors and create a new vector. V plus u. You take the first components add them together. So you get x1 plus x2, comma. You take the second components, add them together. y1 plus y2. Then you take the last components, add them together, you create a new object, which is a vector. So this new object is a vector. If you change addition into subtraction, of course, you can follow the same method by subtracting the first components from each other, the second components from each other, the third components from each other, and create a new vector. We have scalar multiplication. Scalar multiplication. Scalar multiplication is when you multiply a number, a scalar, by a vector. So let's take that scalar to be, I don't know, alpha, any number. Alpha multiplied by v, it is alpha times x1, comma y1, comma z1, which is, what do? Unofficially, we distribute alpha into the vector. Alpha times x1, alpha times y1, and alpha times z1 to create a new vector. Alpha x1, comma, alpha y1, comma, alpha z1, which is a new vector. It means that it has direction and it has magnitude. We define something that we call the dot product or inner product. Dot product or inner product. Well, how does it work? Actually, inner product or dot product, the outcome is not a vector. The outcome is just a number. So suppose we want to find the dot product between v and u. What do? We multiply the first components, x1 times x2. We multiply the second components, y1, y2, and we multiply the last components and add them all together. The outcome is not a vector. This is not a vector. It's just a number, just a scalar. And finally, we introduce cross product between two vectors. Cross product, okay. Cross product between two vectors. The way that we define cross product is when we use the determinant. So what do? The cross product between v and u is denoted by v cross u. It's not the Cartesian product. This guy, the operation between two vectors, is called the cross product. Okay. So we need the determinant. The determinant of what? On the very first row, you're going to use your direction vectors for x-axis, for y-axis, and for z-axis. I, j, and k. The very first vector is v, so you're going to copy down the components of vector v, x1, y1, z1, x1, y1, z1. The very last vector is vector u, so you're going to copy down the components of u, which is x2, y2, z2. From the determinant, you know that this guy is equal to I in the direction of x-axis times, okay, you get y1, z2 minus z1, y2. Then note that we're using negative j. It's not a plus sign. Minus j in the direction of y-axis. Well, in the direction of y-axis, we deal with x1, x2, z1, z2. So it is x1, z2 minus x2, x2, z1. And finally, in the direction of z-axis, plus k, x1, y2 minus x2, y1, following the definition of determinant. We call that I is a unit vector. It means that the length of the vector is 1, and this is denoted by 1, 0, 0. This vector is the vector that we use to represent x-axis. J is vector 0, 1, and 0, representing y-axis, and z-axis represented by k, which is 0, 0, and 1. Very well. So, from our recall, what is a unit vector? A unit vector is a vector that its magnitude is 1. But unfortunately, not all vectors have magnitude 1. In many cases, you need vectors with magnitude or length 1 for simplicity. A unit vector is a vector with length equal to 1. So if U is a unit vector, it means that its magnitude is equal to 1. What if you have a vector and the magnitude of that vector is not 1? Can we make it a unit vector? Note that if V equals to X, Y, Z is not a unit vector, we can scale this vector and create a new object with length equals to 1 and create a new vector with length equals to 1. But how? To do that, we divide each component of vector V by the magnitude of vector V. That way, we create a unit vector. So V, vector V, divided by its magnitude, which is now x over square root of x squared plus y squared plus z squared, comma, y over square root of x squared plus y squared plus z squared, comma z over square root of x squared plus y squared plus z squared is a unit vector. Another note, if you have two vectors like u and v, like u and v be two vectors, then the theta, the angle between those two vectors, its cosine is equal to the dot product between u and v divided by the magnitude of u times the magnitude of v, or the dot product between u and v. If we have theta, the angle between them is going to be the magnitude of u times the magnitude of v times the cosine theta. From this formula, if you have two orthogonal or perpendicular vector, if you have perpendicular vector, two vectors are perpendicular to each other, it means that the angle between them is 90 degrees or pi over 2. In that case, the cosine of 90 degrees is equal to 0. So the dot product is 0. This is another note for you. So if you have two vectors, make sure that they are orthogonal or perpendicular to each other. You can find the dot product. If the dot product is equal to 0, then we say that, hey, those two vectors are perpendicular or orthogonal to each other. So what about the sine of the angle between two vectors? The sine of the angle between two vectors has to do with the magnitude of the cross product. So we have the cross product between u and v divided by the magnitude of u times the magnitude of v. Or if the question says, hey, find the magnitude of the cross product between two vectors, and you already know what theta is, you can use it. You have the magnitude of u times the magnitude of v times sine theta. Very well. We can also project a vector over another vector. The vector projection of vector, for example, v on vector u. So suppose v is, let me just write down this for you. V is x1, y1, z1 on u, x2, y2, z2 is the projection of B onto A, which is equal to A dot B divided by the length of V dot U, divided by the magnitude of V squared times over U. So we're going to have the magnitude of U squared times vector U. The order is not important here, and let me just write this guy vector V over vector U. So this is going to be a new vector. Suppose you have your vector U here, and here you have your vector V. You're going to project vector V over U. And this is the cosine theta. It's cosine. This is going to be the projection of V over U. And to find this new vector, you're going to follow the formula V dot U or U dot V, it doesn't matter, divided by the length of U squared times vector U. So the result is a vector. Okay, very well. So we talked about vectors, we talked about operations between vectors. Now we're going to expand our knowledge to lines and planes and eventually surfaces in the space. This is our goal. Lines and planes. (12.5), 12.6. So we're going to focus on lines first. How do we define lines in the space? We have different methods defining lines in the space, depending on what information is given to us. Very well. Parametric equation. When you're talking about lines and we're talking about parametric equation of the line, it means that you're introducing a parameter. Well, in this case, we need 1 point on the line, and also we need a direction vector. What we need 1 point on the line, and we also need a direction vector. We need the direction vector. So how does it work? So suppose you have 1 point, this is your point, And you already know a direction vector like V in the space. How do we write equation of the line passing through this point? This is given to us. The point is also given to us. We want to know what is this equation. Very well. To write the equation of the line, we have x, y, z. Let's write down this point here as x sub 0, y sub 0, z sub 0. So note that I'm using parentheses to represent this point. And for this vector, I'm going to use A, B, and C. So vector A, comma B, comma C. The components of this vector are A, B, and C. This is your vector in the space. So equation of the line in parametric form. It has x, it has y, it has z, which is equal to the point represented as a vector x sub 0, y sub 0, z sub 0, plus your parameter t times the components of your vector, direction vector A, B, C. So what do we have? We have point, and we connect the point to the origin to represent a vector plus t times the direction vector. We usually represent this guy this way. We say that, hey, x, y, and z is equal to x sub 0 plus at, comma, y sub 0 plus bt, comma, z sub 0 plus ct. Or we write it this way. We say that, hey, the x component of the line, x is equal to x sub 0 plus at. The y component of the line is y sub 0 plus bt. And finally, the last component, the z component of your line, is z sub 0 plus ct. Perfect. This is our x-axis, for example. This is our y-axis, and this is our z. Suppose this is your point, x sub 0, y sub 0, and z sub 0. So what do we do? To define this as vector, we are connecting the origin to the initial point or the point on the line. So at the same time, you know that you have a direction vector. Okay, in this direction vector is given to us. This is our vector V, A, B, and C. This is going to be your line. So it means that if I take any other point on this line with x, y, z as its coordinates, I can just construct a new vector, this new vector, which is vector x, y, and z. So I have vector x, y, and z. I have this vector, which is x sub 0, y sub 0, z sub 0 here. Just continue this guy here. So you know that we are going toward this direction for our line. So here you have three vectors, x sub 0, y sub 0, z sub 0. Then you have vector a, b, c. And then here you have x, y, and z. But note that this vector as v, it has a specific length. When it comes to line, it's stretched. It's stretched. So it means that if you multiply this by a parameter like t, you can stretch this, scale this guy over L. So what do we have here? We have the sum of these two vectors equals to this vector. Okay, but we know that it's not just a piece of line. It's the whole line itself, which we multiply by t. So x sub 0 and comma y sub 0. Let's write this guy separately. Z sub 0 plus the parameter times v, which represents this line, t times a, b, c, which is equal to this length here, this vector here, x, y, and z. So this is the geometry behind the formula for parametric equation of your line.